Today we're going to look at how to solve simultaneous equations, which just means there's more than one. So we've got two different equations and we're going to solve them two different ways. We're going to solve them graphically and we're going to solve them algebraically. So graphically is just drawing them both on the same graph and seeing where they cross. So the first thing I'm going to do is rearrange my equations to be in the right form. Y equals mx plus c. So I just want to get y by itself. So y equals negative x plus 7. Obviously I bring this over as a minus, and then I'm just going to put it in the right order. This one here, negative y equals negative x plus 3. So then if I need to get y by itself, y equals x minus 3. I'm just going to cross this out so we don't get confused, but that was just the middle step. So now this is 1 and 2. So all I'm going to do is plot them both and then see where they end up. So this, remember, the first thing we always do is the y-intercept. So it's 7, 1, 2, 3, 4, 5, 6, 7. And then the slope is negative 1. So I go down 1 over 1, down 1 over 1, blah, blah, blah. Okay. Now, you're going to have a ruler and you're going to do a lovely job of this. Okay, so the next thing I'm going to do is this one. Same thing, my y-intercept is negative 3, 1, 2, 3. And then same thing, the slope is positive 1, so I go up 1 over 1. And then that means all of these things are my points. So my point of intersection is right here. This is where they equal each other because it's where they hit on the graph. So 1, 2, 3, 4, 5, 3. So the coordinates, or when these two equations equal the same thing, is at the point 5, 3. Now, there is another way that we can solve this without having to draw a graph, and that's by doing it algebraically. So I'm going to write them down again. So x plus y equals 7 and x minus y equals 3. So what I'm going to do is I'm either going to add them or subtract them to get rid of one of the variables. Now, for this one, it doesn't matter because if I add them, then y disappears because y plus negative y is 0. And if I subtract them, x minus x is 0. So it doesn't really matter. I'm just going to add them because I can. It really doesn't matter. So x plus x is 2x. Y plus negative y is 0, so that doesn't matter. And then 7 plus 3 is 10. So x equals 5. And then all I do is substitute this back into one of these. Oh, and it looks like I've made a mistake on my graph. Oh, why did I write that was 3? Oh, that should be 2, shouldn't it? There's my problem. All right, then I substitute this value back into either equation, it doesn't matter. 5 plus y equals 7, so y equals 2. And see, that's what I got here, isn't it? 5 and 2 were my solutions, so it works algebraically and graphically. All right, let's try it with slightly different numbers. This one's going to be trickier, but it's the same process. So the first thing I'm going to do is rearrange them to look like y equals mx plus c so I can graph them. So for the first one, I'm going to have negative 5y equals negative 4x plus 1. And then I'm going to have y equals 4/5 x minus 1/5. Now, this is clearly a rubbish equation in terms of plotting things accurately. Negative 1/5 is like here, which is just so inaccurate. I really don't like what this is going to look like, but we'll see in a second. So then the second one here is going to be y equals negative 2x minus 3. Much, much easier. Minus 3. So anyway, let's plot this first. So negative 1/5 is roughly there. And then I'm going to rise over run. So rise 4, run 5. So 1, 2, 3, 4, 1, 2, 3, 4, 5. So really it's about there. So this is a bit of an estimate because I had to use the fifth. Okay, and then this one, the y-intercept is negative 3, 1, 2, 3, and my slope is negative 2, so down 2 over 1. So it looks like it crosses, hopefully exactly there, but we'll find out. So to me, this looks like it crosses exactly there, which is negative 1, negative 1, and we're about to check that algebraically. So I'm going to write my two equations again. So 1 is 4x minus 5y equals 1, and 2 is 2x plus y equals negative 3. Now, there is no way for me to add or subtract these two equations together to actually eliminate either x or y. So what I'm going to have to do is make one of the numbers equal each other. sorry, make one of the terms, so either y's or x's. So what I can do is I can double this equation because that'll turn this into 4x, or I could times it by 5 because that'll get it to 5y. It really doesn't matter which one you choose. I'm just going to double this one because it seems a bit simpler. So then I have 4x minus 5y equals 1, and this new equation doubled is 4x plus 2y equals negative 6. So I've got to double everything. So now I'm dealing with these two. Now I'm going to subtract one from the other because 4x minus 4x is 0, so that works. So this is negative 5y minus 2y, which is negative 7y. 1 minus negative 6. So remember, you're subtracting and it's already negative, so that gives us 7. So y is negative 1. Look at that. That's exactly what we wanted. Then I just substitute it into any of the equations. So I might just put it back into the first one because why not? So 4x minus 5 times negative 1 equals 1. So 4x plus 5 equals 1. 4x equals 1 minus 5 is negative 4. So x equals negative 1. Look at that. It's exactly what we said graphically. So this method is a little bit trickier. We might just do another practice of that because I think you guys know how to graph by now, and solving simultaneous equations is just looking at the graph. But this is a little bit trickier, so I might just come up with a couple of more equations so we can practice. So let's say this one is 3x plus 4y equals 12. And this one here can be 2x minus 6y equals 2. All right, so now there's nothing I can do that is going to make one of these equations equal the other. So what I'm actually going to do is manipulate both of them. So I am going to times this whole equation by 2 and this whole equation by 3, because that means my x's will both look like 6. So as long as I'm consistent, I can do whatever I like. So I'm going to double the first equation, 6x plus 8y equals 24. And then I'm going to triple the second equation, 6x minus 18y equals 6. Now I'm going to subtract these because 6 minus 6 is 0. So that's going to get me to eliminate one of the variables. So then I have 8 minus negative 18. So 8 minus 18 is going to be 26y, and I'm subtracting these, so 24 minus 6 gives us 18. So then y equals 18 over 26. Now obviously we've got some terrible fractions here, 9/13, but that's all right. We're allowed to have fractions, we're allowed to have difficult answers. And then I just take this and substitute it back into any equation. I'll just pick the first one because I can. So 3x plus 4 times 9/13 equals 12. Now, of course, we're going to get some horrifying answer here. 36, whoops, why did I put an equal sign there? 36/13 equals 12, blah, blah, blah. You can keep going, you get my point. But the whole purpose of this is to figure out how you can eliminate one of the variables. Let's do a slightly simpler one where we're not going to end up with terrible fractions because I made it up as I went. Let's do something. Actually, I can't promise that's going to happen because I can't be bothered working it out. But let's do it again. So x minus 3y equals 10. And then I'm going to make this one 2x plus y equals 4. All right, so this time I only need to multiply one of them. So I could multiply this one by 2 to get them to 2x, or I could multiply this one by 3. So either that one by 2 or this one by 3, because that would make this 3y. Again, it does not matter which one you do. I'm just going to double the top one. And then the second one I'm going to leave alone. Okay, now I'm going to put them together. So I'm going to subtract again because 2x minus 2x is 0. So then 6y minus y is negative 7y. And then 20 minus 4 is 16. So then y is 16 over negative 7. And then again, you just plug it straight back in to get your x value. Now, like I said, these are terrible fractions. The book is basically giving you things more like this, where you get exact whole number answers. Because whilst this works really well algebraically, this would be impossible to check on a graph, because you'd be like, well, I guess it looks like it's about there. But for these ones, they cross exactly in the right place, which is why you need to use a ruler and why you need to use graph paper, because otherwise it won't cross exactly. Okay, let me know if you need any help. Good luck with this one.